Alright, so today we'll be looking at section 14.7, the other inverse trigonometric functions. In 14.6 we looked at inverse sine and inverse cosine. Today we'll look at the other four, which are inverse tangent, inverse cotangent, inverse secant, and inverse cosecant. The first thing I want to show you is the graph of y equals the tangent of x. You notice that the range of this function is pretty much from negative infinity to infinity. And the domain includes all real numbers that are not odd multiples of pi over 2. So you will now see that for it to have an inverse, we have to turn it into a one-to-one function, just like we did with sine and cosine. So this part in blue suggests the range of the inverse tangent function. So the range will be between negative pi over 2 and pi over 2. The domain, as you can see, for the inverse is pretty much going to be all real numbers, but the range will be limited to the blue. We'll show you the graph in a moment. The inverse tangent of x, y equals the inverse tangent of x if and only if the tangent of y equals x and negative pi over 2 is less than or equal to y is less than or equal to 2. So again, the range is between negative pi over 2 and pi over 2. And if we take a look at the graph, there it is. Again, it is the tangent function turned sideways a little bit. Notice that it's negative when x is less than 0 and positive when x is greater than 0. And we had to limit the range from negative pi over 2 to pi over 2, otherwise we're going to have different potential values of y. So that is the inverse tangent graph. The graph of the cotangent of x is the same deal, except here your suggested range for the inverse cotangent is going to be between 0 and pi. So something very similar going on as we had with tangent of x. So the y is the inverse cotangent of x if and only if the cotangent of y equals x and 0 is less than or equal to y is less than or equal to pi. So cotangent has a similar domain / range as cosine, and sine and tangent have similar. So in that cotangent's range is between 0 and pi, tangent's range is between negative pi over 2 to pi over 2. So here's your graph for the inverse cotangent. You can see that it's going to start out positive, and as it crosses pi over 2, it goes down towards 0. And if we did not have the capital C for the inverse cotangent limiting the range from 0 to pi, you would have other values that could satisfy the function. Alright, let's take a look at some examples. These aren't too bad to start. The inverse cotangent of radical 3 over 3. So remember that the solution for this must be between 0 and pi. So for what value of y does the inverse cotangent equal radical 3 over 3? Thus, the cotangent of y equals radical 3 over 3. So what value of y does that equal? Y is pi over 3, and so the inverse cotangent of root 3 over 3 is pi over 3. I might have misspoke earlier. Let y equals the inverse cotangent of radical 3 over 3, then set cotangent of y equals root 3 over 3 and solve for y. Now again, just like with the inverse sine and inverse cosine, you don't necessarily have to go through each step. If you know the angle, you know the radian, plug that in and you'll be fine. Example 2, the inverse tangent of radical 3. So same deal. The solution here must be between negative pi over 2 and pi over 2. So we let y equals the inverse tangent of root 3 such that the tangent of y equals root 3. So what angle y does the tangent equal root 3? Well, between the first and fourth quadrant, the answer would be pi over 3. So the inverse tangent of radical 3 is pi over 3. Now you will notice that for the inverse cotangent of x and the inverse tangent of x, they are related. And you can see the relationship here. The inverse cotangent of x is equal to the inverse tangent of 1 over x. And there's a proof in the book on page 693, which I'm not going to show you, but if you want to look at it for your reference, you could do it. This will allow you to easily convert between cotangent, inverse cotangent, and inverse tangent. and is with the same principle that we give you the definition for inverse secant and inverse cosecant. So, if the absolute value of x is greater than 1, then the inverse secant of x equals the inverse cosine of 1 over x. The inverse cosecant of x is equal to the inverse sine of 1 over x. Let's take a look at example 3, the inverse secant of root 2. So, remember that the inverse secant of x is equal to the inverse cosine of 1 over x. So, the inverse secant of root 2 is equal to the inverse cosine of 1 over root 2, which is the reciprocal of root 2. And that's equal to radical 2 over 2. So, again, for inverse cosine, we're looking for a value between 0 and pi, and the answer would be pi over 4. Alright, now we're going to get some more involved examples. Number 4, the cotangent of the inverse cosecant of 13 over 12. So, first thing we can do is convert the inverse cosecant of 13 over 12 to the inverse sine of its reciprocal, or 12/13. If we let y equal the inverse sine of 12/13, the sine of y equals 12/13. Now we can solve for the cosine of y using the identity sine squared y plus cosine squared y equals 1. If we use that identity and solve for cosine y, we get 1 minus the sine squared of y, or the square root of 1 minus 12/13 squared. I will tell you that that ends up being 25 over 169, which simplifies into 5/13. Now, you might remember, what does cotangent equal? Well, cotangent equals cosine over sine. Well, we now know the cosine of y is 5/13. We already figured out the sine of y was 12/13, and so now we divide 5/13 by 12/13. The 13s cancel, and you're left with 5/12. So, when you're given an inverse cosecant or inverse secant, sometimes it makes it easier to take the inverse secant, to convert it to an inverse cosine and take the reciprocal, and then you'll often be able to figure out sine or cosine using the basic Pythagorean identity of sine squared x plus cosine squared x equals 1. Example 5. The inverse cosecant of the cosecant of negative 3 pi over 4. You can try this one and then come back for an answer. So the first part I want to do is the inside of the parentheses. What's the cosecant of negative 3 pi over 4? Well, negative 3 pi over 4 is in the third quadrant, so you're going to have a negative number because y is negative in the third quadrant. And that turns out to be negative radical 2. Now you will remember that if you just can't remember the cosecants, remember the sine. The sine of negative 3 pi over 4 is negative radical 2 over 2. Then just take the reciprocal, which is in this case negative radical 2. Now, since we have the inside of the parentheses, we can now go on to find the inverse cosecant of radical 2 over 2. And because the range of inverse cosecant is between negative pi over 2 and pi over 2, we can take the inverse sine of that, which is negative pi over 4. So you'll notice that the answer is not the same as the negative 3 pi over 4 here, because that's not within the allotted range of inverse cosecant or inverse sine. The allotted range is negative pi over 2 to pi over 2, and negative 3 pi over 4 falls out of it, which is why you have to do each step. Negative pi over 4 falls within the accepted range. Example 6. Cosine of 2 times the inverse tangent of 2 root 2. The first thing you're going to have to notice is that you're going to use some sort of trigonometric formula. You might be able to see it, and if you don't, here it is. Remember that the cosine of 2x is equal to 2 times the cosine squared x minus 1. It's also cosine squared x minus sine squared x, or 1 minus 2 sine squared x. I just chose cosine squared x. You'll probably want to choose either that one or the one with 1 minus 2 sine squared, and you'll see why in a moment. So if we expand that using the 2 cosine squared x minus 1, this is what you get. The original expression is equal to 2 times the cosine squared of the inverse tangent of 2 root 2 minus 1. Since the inverse tangent of 2 root 2 is what it is, we know that it reflects the y over x, because that's what tangent is. It's sine over cosine, y over x. Remember, tangent theta equals sine theta over cosine theta, and r sine theta over r cosine theta is tangent. So we can set the 2 root 2 over 1 and let that equal y over x at its most basic level. So we can now solve for r, because r is the square root of x squared plus y squared. 2 root 2 squared is 8, 1 squared is 1, so we have r is 3 in this case, which will represent the hypotenuse in a right triangle. If you do that, remember that the cosine is x over r, so in this case, the inverse tangent of 2 root 2 is equal to the inverse cosine of 1 over 3. That's the x over r. So the angles are the same, just different trigonometric inverse expressions of that angle. So now we can plug in the inverse cosine of 1/3 and substitute that for the inverse tangent of 2 root 2. So your equation or expression becomes 2 cosine squared of the inverse cosine of 1/3 all minus 1. Well, we know that cosine of the inverse cosine of 1/3 is 1/3. So we have 2 times 1/3 squared all minus 1. 1/3 squared is 1/9. 2 times 1/9 is 2/9. 2/9 minus 9/9 yields you negative 7/9. So when you see a question like this, first see if there's a double angle, half angle, or some addition formula or subtraction formula, and then convert the inverse tangent into an inverse cosine or something else that will help you solve the problem. Plug in and solve. Example 7. Tangent of the inverse tangent of negative 4/3 plus the inverse tangent of negative 1/7. Alright, another trigonometric formula you'll have to use here. Which one is it? It's the tangent sum formula. So, in case you've forgotten, the tangent of a plus b equals tangent of a plus the tangent of b all over 1 tangent a times tangent b. So, playing the role of a is the inverse tangent of negative 4/3, which goes here. Playing the role of the letter b would be the inverse tangent of negative 1/7, and they are multiplied together here. And I guess that does seem like a bit of a mess, but let's see what we can do with this. So remember that tangent of the inverse tangent of negative 4/3 is just negative 4/3. The tangent of the inverse tangent of negative 1/7 is negative 1/7. So in the numerator you have negative 4/3 minus 1/7. In the denominator, remember, is 1 minus tangent of a times tangent of b. So here 1 minus negative 4/3 times negative 1/7. Now we simplify the fractions, and you get negative 28 minus 3 over 21 all over 1 minus 4 over 21. And so if you reduce the fraction, you get negative 31 all over 17, because the denominators of 21 cancel out. So again, use the addition formula, plug in the values. This one's not too bad. Example 8, our last one. The cosine of the inverse cosecant of negative 1 plus the inverse secant of 17/15. So again, you will want to start out with some sort of addition formula or double or half angle formula. In this case, it's the addition formula. Remember, the cosine of a plus b is equal to cosine a cosine b minus cosine a cosine b. So here is the expression using that addition formula. So the cosine of the inverse cosecant of negative 1 times the cosine of the inverse secant of 17/15 minus sine of the inverse cosecant of negative 1 times the sine of the inverse secant of 17/15. We can knock some of these values out right away. First of all, we can figure out that the inverse cosecant of negative 1 is negative pi over 2. Remember, the range of the inverse cosecant is from negative pi over 2 to pi over 2. Negative 1 is at the beginning of that short curve. So let's substitute in negative pi over 2 for the inverse cosecant of negative 1, and this is what we get. The cosine of negative pi over 2 is 0, because that's like the cosine of negative 90 or the cosine of 270 is 0. Meanwhile, for the sine of negative pi over 2, negative pi over 2 is in the quadrantal between the third and fourth quadrants, so it's going to be negative 1. So the first expression disappears because the cosine of negative pi over 2 is 0. So we have 0 minus negative 1 times sine of the inverse secant of 17/15, which we haven't tackled yet. If you knock out the 0 and flip the sign over, that expression at the beginning equals sine of the inverse secant of 17/15. So remember, the inverse secant of 17/15 is equal to the inverse cosine of its reciprocal, which in this case is 15/17. Now we have to solve for r using sine squared y plus cosine squared y. And to figure out sine y, we do the square root of 1 minus the square of cosine y, which is 1 minus 15/17 squared. That equals 8/17, 64 over 289. So that gives you a start on example 8. Let's go to the finish. So we now know that the inverse secant of 17/15 is equal to the inverse sine of 8/17. Now we can substitute that in there to help solve our problem. Now we have the sine of the inverse sine of 8/17. We know that the sine and the inverse sine just kind of cancel each other out, so you're left with 8/17. So a lot of review of the double angle, half angle, summation, addition, subtraction formulas, plus a healthy dose of trig, and just some patience. So you can use the book method if you want. If it's faster for you to just memorize things or crank things out in your own way, that's fine too. We'll do problems in class on Wednesday, and if you have any problems in the meantime, send me an email, post on Facebook, or talk to me the next day in class.